For our term project, we found an article entitled Efficient Algorithms for Fixed Point Arithmetic Operation in an Embedded PIM. A PIM, or Processing in Memory, integrates a processor onto a chip using dynamic RAM, which increases bandwidth between processor and memory speeds. One of the major issues in regards to floating point arithmetic operations in PIMs is the growing difference between processor and memory speeds. One of the approaches for fixing this problem is inserting a processor into memory, increasing the speed of execution by reducing the distance between stages. Our project will go over one of the methods published in this paper for increasing support for fixed point arithmetic using integer arithmetic. Fixed point representations, as a review, can be used to represent numbers such as 1, 2, or 3. Floating point numbers have a much wider range of values and can be used to represent fractional numbers. Here we have the pseudocode for the algorithm as presented in the paper. As you can see, we separate our number and process it in multiple places. We are converting 43.75 into an integer representation as our hardware does not support floating point numbers. 43.75 is then equivalent to 175. This can be represented in binary as 10101111. As part of our algorithm, we shift this number to the right 2 places in which the decimal is now 43.75 times 43.75. This seems like undoing our work, but it is a simple workaround for our hardware issue. We then multiply p by 2. The first instruction is AI is equal to shift right AP. Shifting 10101111 by 4 to the right leaves 1010. We then store the shifted out bits into AF, so AF is equal to 1111. We then duplicate this so that both numbers are equivalent. We then shift the product of AF times BF by P. So 1111 times 1111 gives us 1110, or 14. We now multiply AI and B, or 15 times 175, which equals 1750. We then multiply AF and BI, which gives us 15 times 10, or 150. Lastly, we add the 3 results. This gives us 14 plus 1750 plus 150, which gives us our final answer of 1914. So this is our C implementation of the code. As you can see, this is A and B. We set our P part here. We then call our shift function with these values. We then split the values here, getting the component values. We then return the modified values multiplied and added together to achieve an integer. And now we will run it. As you can see, all the values add up, giving us our final answer of 1914.